Let's do some nuclear reactions with binding energy per nucleon, right? So let's write this reaction out normally. So 4019 potassium plus a proton, that's going to be a 1,1 hydrogen, right? Turns into 1,0 neutron plus 4020 calcium 20. It's transmutating the elements, right? So our energy here, potassium 40 has this per nucleon, notice that, right? It's got 40 nucleons, so its energy is going to be 40 times 8.538 MeV, right? Okay. Plus, and I'm just sort of going to pause there, right? Notice we have a single hydrogen atom there, right? Its binding energy is 0 because it's not bound to anything, right? Same thing's true for a or actually we'll say what goes to this, right? Same thing's true for a neutron. It's not bound to anything. There's no binding energy, right? Basically, we'd go the neutron mass minus the neutron mass times 931.5, which would give us 0, right? And then this guy, calcium 40, it's 40 times 8.551, right? So now we just plug this in, right? 40 times 8.538. I'm going to type in the next number, 538. I'll go 1, basically, right? Minus 40 times 8.513, roughly, right? And I get that we lost 0.528 joules of binding energy. Or MeV, sorry. Right? And so since I'm trying to figure this out. It's exothermic. Why is it exothermic? Because it seems like we would want to go to more tightly bound. Oh, it is more tightly bound. Yes, it is. This is more tightly bound. So we went to more tightly bound, so therefore it's exothermic. All right, I got it. Yep. Oh, I've got it, right? So if you increase the binding energy, you release energy, okay? And we're a little bit off, and that's because this isn't really how you do nuclear reactions. We did this one before as a nuclear example.